Namaste. Let us start the lectures of week 11. In this week, we will start talking about the characterization tools which are used for understanding the properties of nanomaterials. If you look back through the whole course which we have discussed in the first 10 weeks, what have we done? We started with the concept that there are materials which can be of various shapes and sizes. And when you take the dimensions of bulk materials in the range of 1 to 100 nanometers, dimensions, either one of the dimensions or two of the dimensions or all the three dimensions are in the range of 1 to 100 nanometers. Then we get a new set of materials which are classified in the heading nanomaterials. And similarly, you can talk about devices. The need for such classification or defining a new set of materials came because we saw that the properties, both physical as well as chemical, changed significantly from those which were observed when the particles were of larger size. And with that came the development of the field of nanomaterials and nanotechnology, and today we find this field, that is comprising both of nanomaterials and nanotechnology, in and around us everywhere. So, it is also now imperative that we actually understand how do we characterize these nanomaterials. We have always been saying that there is a nanomaterial which is formed. Where is the proof? The proof will come from characterizing these materials. We have been saying that as you change the morphologies, the properties change. Again, where is the proof? We must understand that when you make materials using different types of synthesis routes under different thermodynamical parameters, then their shapes and sizes can change. We should have the capability to understand that these modulations in the shapes and sizes will impact the properties. So, first we should develop the capacities to analyze, visualize and collect the right information about the morphologies of the particles. And once we do that, then there must be some ways where we will be understanding about the physical as well as the chemical properties of these systems. Then we can move on and talk about the mechanical properties, electrical properties, optical properties, optoelectronic properties, magnetic properties, spintronic properties, charge storage properties, and so on and so forth. And then we have to correlate the response characteristics with the intrinsic properties of the material which is being used in a given application. The properties which we use to correlate would be the shape and the size of the particles and the types of particles. Are they clusters? Are they the ones which are arrays? Are they self assembled? Are they homogeneously distributed? Are they agglomerated particles? And then we will develop the overall picture. So, let us today give you some of the basic information about the characterization tools which are used to investigate the structural, spectroscopic, optical, thermal to compositional and elemental analysis of these nanomaterials. It is important that we talk about most of these techniques. The question someone may ask is why? Why so many techniques? It is very important that we rule out the response characteristics to the possibility of having an extrinsic effect. What I mean by that is that you may get one data, one characterization data, for example, just structural, and based on that we try to explain all the properties which are observed in the material you have synthesized. But directly from structural analysis, for example, using electron diffraction, neutron diffraction, X-ray diffraction, from there it may not be possible to give you the information about the distribution of elements in a given particle. Is the system having homogeneous distribution of the elements, or you have inhomogeneous distribution of elements? For example, if you are trying to make a material like AbO3, then they should be homogeneously distributed so that you can get the perovskite type building block, that is the unit cell. So, you have B in the middle, A at the cube edges and oxygens at the body center, face centers, and B at the body center. But suppose you do not have homogeneous distribution, then you may get all the B atoms or oxygen atoms distribution at one point, and then you will never get the structure you want, and then the properties would be different, and making impure materials day in day out, that means reproducibility of impure materials is next to impossible, because sometime you may have inhomogeneous distribution of one type and in the other cycle you may have the other type. So, it is very important that we correlate the response characteristics using a large number of characterization tools, and the results of each corroborates the findings of the other. And once you have a consistent picture, then only you can give a meaningful information which can be utilized for the technological applications of such materials. So, we will talk about structural, optical, thermal, surface and mechanical characterization of the nanomaterials. Using this, you can find out large number of information which are inbuilt in the characterization tools names. So, again it is a combination of methods which are required to completely understand the response characteristics of nanomaterials. And if you look into some of the commonly used physiochemical techniques, then they are classified under different headings. For example, if you want to collect data about the structural and morphological information about the nanomaterials, then the routinely used techniques are X-ray diffraction, scanning electron microscopy, transmission electron microscopy, tunneling microscope and atomic force microscope, to name a few. If you want to determine the spectroscopic response of the materials which you are synthesizing or you have synthesized, you use techniques like UV visible spectroscopy, IR or FTIR, Raman spectroscopy, XPS, NMR or ESR. Then for optical properties or photophysical properties, you use PL, time resolved optical spectroscopic data, DLS and zeta potential measurements. Thermal analysis, you have TGA, differential scanning colorimetry, DSC and DTA. For mechanical and surface property analysis, you have nano indentation, Bronner Emmett-Teller BET measurements or contact angle measurements. For compositional and elemental analysis, you have EDX or EDS, ICP MS or secondary ion mass spectrometers or spectroscopy called as SIMS. These are just a few. There are many more. You should remember that we have taken some examples only. So, now we have just taken some examples of commonly used techniques. There are many more techniques which are required, because for electrical measurements, magnetic measurements, electrochemical measurements and so on so forth, you will go on adding the characterization tools. Now, as I said in the previous slide, what is required? That one set of data corroborates the findings of the other sets. Then only the material is useful. For example, if thermal analysis tells that the glass transition temperature is around 60 degrees in a given polymer, and then you do a temperature dependent XRD or SEM-TM, then you find that the system is actually remaining intact and there is no evidence of increased amorphization or phase transition up to 200 degrees. Then the two data do not corroborate and hence our findings are incorrect. So, we should be able to consistently explain the findings of one set of data from the measurements which are done under the other subheadings which are mentioned here, and once all of them are giving a consistent picture, then we can move to the application of these materials. Now, you will understand why it takes time to make a material and then use it. Because first, as we had discussed during the synthesis protocols for obtaining nanomaterials, you have to optimize a large number of parameters before you can have the desired materials, which can be reproduced after each synthesis cycle. Now, once you have obtained that capability, you have to now characterize those materials using some of these techniques, which are just a few of the many which are required to characterize these materials. Then you have to take these materials to the application sector, and before that you have to characterize them as per the desired application area. If you are taking for battery, you will take it for electrochemical measurement. If you are taking for spintronics, you will take it for magnetic measurements. If you are taking for electrical sensors, you will take it for electrical measurements. And then only you can start making the devices. And now, once the device is made, you will have to make large number of devices and characterize those devices. And once all the pictures, that is starting from the raw material to synthesis to characterization to application and reproducibility at each step is obtained, then only you can start sending it for certification, and after certification you can send it for field trials, and after field trials you can then send it to commercialization step. So, it takes significant time to take a material from lab to market. For one of the most common techniques which are used for understanding the crystal structure as well as to determine the crystallite size is X-ray diffraction. X-ray diffraction is a non-destructive technique which allows you to determine the crystal structure, determine the strain in the lattice or crystallite size or phase of the material, if there are any texturing which are there to determine texturing, and if you have high resolution data, you may also see coexisting phases, and if you do temperature dependent X-ray, you can also get information about the phase transition in these materials. It operates on the principle of constructive interference of X-rays which have the wavelength in the same order as that of the interatomic distances. So, you have lattice which acts like a diffraction grating, and hence you can see the diffraction taking place, and when you have these diffracted beams adding or superimposing constructively or destructively, you will get peaks or you will get areas where are no peaks observed. So, you get the constructive interference of X-rays diffracted from a periodic or arrays of atoms which are arranged in a given manner, and this diffraction angle is obtained using the Bragg's law, which is given by 2d sin theta is equal to n lambda, where n defines the order of diffraction, or else you can write it as 2d HKL if you want to write in terms of the planes is equal to lambda. And you have the incident source and you have the X-ray detector, which moves on the evolved sphere, and as you move around you get the value of 2 theta, and from there you will get theta, and using this relation you can find out what would be the planes that would be giving you a maxima. And from there you can find about the phase, lattice parameters and crystallite size, and it is one of the most common methods which are used in today's research. You can have powder diffraction, you can have thin film attachments for obtaining the data of the materials which you have synthesized. Then comes scanning and tunneling, then comes scanning electron microscopy and transmission electron microscopy. Here you use an electron beam for either scanning the surface or you collect the information in the transmission mode. So, you in SEM you use a focused ion beam to scan the surface and you detect either the secondary electrons or back scattered electrons. The secondary electrons give you the information about the surface morphology, whereas the back scattered electron gives you the information about the elements which are present in the sample. In comparison, transmission electron microscopy, as the name suggests, you have the transmission of the electron beam through the ultra thin sample, and then you collect the transmitted beam and derive information about the sample. Typically, you can have the scanning electron microscope data which can. Next technique which we use is the set of electron microscopies, which are scanning electron microscope and tunneling electron microscope. Scanning electron microscope is generally used to analyze the surface of the materials, whereas the transmission electron microscopy can be used for analyzing the atomic arrangement as well as the morphology of the particles. In SEM, you can have two types of electrons which are emitted. You can have secondary or backscattered. Secondary electrons are used to determine the surface morphology, whereas the backscattered electrons give you the information about the elements which are present in the material. Whereas, in the transmission electron microscopy, you use the transmitted beam which comes out from the thin sample, and you can analyze up to few nanometer size of materials, or you can even go to the interplanar type fringe patterns which are observed in TEM, but not in SEM, which now if you have FESEM, the field emission scanning electron microscopy, you can go up to, let us say, 30 nanometers or more and get a reasonably high quality data. There are people who are reporting using SEM up to 20 nanometers, but it is sometimes difficult to reach such high resolutions with routinely used SEMs. So, SEM is mostly used for bulk or surface samples. you need a non-conducting sample on top of the insulating materials if those are so. Then you use the surface morphology and topography data to analyze the samples, and then you can also carry out the EDS analysis. Whereas, for internal structure, lattice parameters, presence of defects, more detailed information about the crystallography is obtained using the TEM. And you can have large number of fields where they are being utilized. And this is typically the arrangement of the two apparatus which is used. This is just a schematic, but then you have a physical instrument which is there. We will discuss about them later in this week or maybe the next week. So, you will understand much more about the SEM and TEM. Then you have the scanning tunneling electron microscopy. As the name suggests, you use the concept of electron tunneling. So, what you have a sharp tip and the electrons tunnel between a sharp conductive tip and the sample, and as the nature of tunneling changes, you can go on getting the information about the surface of the sample. So, if the tip is moving, you can find this distance is different. If the tip is moving here, then this distance is different, and so the tip will move according to the size and the shape of the particle, and then you can back calculate by the current which is flowing the nature of the distance between the tip and the sample, and that is then giving you the information about the size and the shape of the particle. So, you have a highly sensitive arrangement between the tip and sample distance, and you can hence go up to atomic scale resolution. STM hence is able to provide finer resolutions in comparison to TEM and SEM, with the ability to actually resolve individual atoms. You can map the surface topography along with the nature of atoms which are constituting the materials. You can hence get information about the local electronic density of states, surface defects, and adsorbed atoms or molecules. Then comes the set for spectroscopic techniques. One of the most common one is UV spectroscopy. Here you use a spectrometer that can be used for analyzing the optical emissions, and then you can have either the absorption in the UV range or in the visible range. It is basically based on what? Excitation of electron from the ground state to an excited state when the molecules absorb a specific wavelength or a set of wavelengths. And then there is de-excitation, and you can get the information about the energy levels in these materials. And you use the Beer-Lambert's law, which is given by A is equal to epsilon CL, where E is the epsilon is the molar absorptivity, C is the concentration of the solution, L is the path length of the cell. And then you compare the information from the reference and the sample. So, you have the beam which falls, then you have the beam splitter, it gives you the emission from the reference, and then you also get an emission from the sample. So, then you eliminate the information from the reference, and the additional peaks or information which is there in the spectrum is then designated to the sample. You can have IR or Fourier transform of IR, that is called as FTIR, Fourier transform infrared spectroscopy. And then there is a difference. In IR, it records spectrum one wavelength at a time, but in FTIR, you can actually record all wavelengths at once, and you can improve the speed and accuracy because you take the Fourier transform of the data, and therefore, any inflections or slight peaks or change in the slope become more prominent in the Fourier transform, and hence you get more information about the sample, and you also are able to get higher resolutions. For example, if you take the IR fingerprint of various bonds, so there are various wave numbers where the samples will give you their fingerprints. So, you have different stretching bonds which are observed for different types of bonding. So, if you have triple bonded C atoms, or you have carbon triply bonded with nitrogen, you have a CH stretching mode, then you can see that they come in different wave number range, and you can easily find out that if these kind of features are there, then they are coming due to which kind of bonding. And if the size of the sample changes the nature of the bonding, the shift, either the red shift or the blue shift, gives you the information about the size dependent emissions. Then comes the Raman spectra, and you can use this spectroscopic measurement technique to find out about the inelastic scattering which is associated to the molecular vibrations in the sample, and it is linked directly to the sample, and it provides the molecular fingerprint of the sample. So, if you have an incident photon which gives you scattered photons which are inelastic in nature, then you will have appearance of two types of lines, Stokes and anti-Stokes, leading to shift in energy, and that is directly linked to the sample or the atoms which are constituting the material. You can have molecular vibrations, you can have stretching modes or bending modes, you can have symmetrical stretching or anti-symmetrical stretching, you can have bending modes in plane or out of plane, you can have wedging or twisting, you can have rocking or scissoring modes in plane. And that clearly tells you if these are atoms, and if you can analyze these kind of modes, then you know the nature in which the atoms are rearranging, and you can get direct information about the lattice or the arrays which are constituting a particle. And hence, if there are any change in these features, you can directly correlate with the shape and size variations. Typically, if you look into the vibrational modes in molecules, they are denoted by A, B, E, T, etc., which basically gives you the molecular point groups. And you, for example, if you have A1G, this means you have a acoustic mode which is symmetric with respect to the inversion center. If you have an A1U mode, then that means you have an antisymmetric with respect to the inversion centers. And these numeric substrate are used to distinguish multiple modes of the same symmetry. You can have A1G, A2G and so on and so forth, and that is defining the multiple modes of the same symmetry in the material. For example, if you look into materials, then they have well defined fingerprints. Like for example, if you use graphene or carbon nanotubes or graphitic materials, the G band is approximately at 1580 centimeter inverse, which originates from the in plane stretching of the sp2 hybridized CC bonds. The D band appears around 1350 centimeter inverse, the 2D band is around 2700 centimeter inverse, and the D plus G band is coming around 2950 centimeter inverse, and that gives you defect plus graphitic mode kind of information. So, just by analyzing the spectrum, you can get lot of information about the materials. Then you can have optical and photophysical techniques like PL, you have time resolved spectroscopy, and the process is excitation, relaxation, radiative combinations. So, excitation followed by relaxations or radiative combination, which will give you information about the band gap, exciton behavior, defect states or recombination pathways, and there immediately you can find out that these informations are extremely useful for semiconductor or nanomaterials where defects play a critical role. And you can have time resolved spectroscopy, that means you can monitor the excited state dynamics over a period of time, and from there you can find out the information about carrier lifetime, recombination mechanisms, energy transfer dynamics, and these are extremely important for photovoltaics and optoelectric properties. Then you can have dynamic light scattering measurements, DLS measurements, which are used to analyze the stability of colloidal systems or aggregation studies, homogeneity of particle distributions, and is based on the Brownian motion and Stokes-Einstein relation. We will talk about DLS and zeta potential in coming lectures. These are extremely useful to find out the stability of these particles and interparticle interactions. The thermal analysis is used to find out the thermal properties of these materials, meaning the stability of these materials as a function of temperature variation or changes which can be observed in these particles as a function of changing temperature. You have the thermogravimetric analysis, that is TGA, where you measure the change in the mass of the sample as a function of temperature. For example, if you heat a sample and there is a continuous evolution of some gaseous components, then the mass of the sample will go on reducing, and then you will know that what is the content of such volatile components. If there is water inside, then water will go on leaving the sample as you heat the sample above room temperature, and above 100 degrees the water will evaporate out. But because you have bounded water, you may see water coming out of the sample at temperatures even higher than 100 degrees, but then you can find out in what range water leaves the sample, and hence you can find out about the decomposition kinetics, thermal stability, composition, and this is one of the most used techniques to characterize polymers, composites, nanomaterials, biomass, and also to understand the chemical reactions like oxidation, degradation, and combustions. Then you have differential scanning calorimetry, which measures the heat flow difference between the sample and the reference under control temperature. And then you can find out whether there are any exothermic or endothermic reactions taking place in the sample as a function of temperature, and from there you can find out information about the glass transition, melting points, and these parameters then will give you the information about the crystallization, heat capacity, or enthalpy changes which may occur in a given sample. Then you have DTA, that is differential thermal analysis. Again, it measures the temperature difference between the sample and the reference, but under identical thermal cycles. And the principle is that phase transitions cause peaks in temperature difference versus time and temperature plots. So, from there you can get the information about the glass transition temperature, melting temperatures, you can have transition temperatures, you can get information about dehydration and decomposition points, or endothermic and exothermic reactions. And hence, DTA is extremely useful for ceramics, clays, mineral analysis, or even phase identification in inorganic materials. And it acts as a complementary tool to TGA and TSC. Then you have mechanical and surface property analysis of different materials, and these are carried out using techniques such as nano indentation, where you determine the mechanical properties at the macro as well as nano scale. Here, a sharp indentator, often made of diamond, is pressed to the surface. So, you have a sharp indenter which is pressing the sample under a precisely controlled load, and then you get a load displacement curve and find out the hardness, Young's modulus, any failure, fracture, creep behavior, or you can find out viscoelastic properties in the samples. And hence, these are extremely used in thin films, coatings, or nanomaterials, because these properties will define the utilization of the materials which we have studied in the area of microelectronics, bio devices or biotechnological applications, and in various structural material research which are going to be utilized for their strength. You can find out about the specific surface area, porosity, the nature of pores in the samples using the BET analysis, which is based on the adsorption-desorption curve, or it is also based on adsorption-desorption of nitrogen or other inert gases at different relative pressures. Then you plot the adsorption-desorption isotherms, and from there you can use the BET equation to find out the surface area, the pore volume and pore size distribution in these solid materials, and this information is extremely important before a nanomaterial can be utilized. If you want to determine the wettability of a material, then you use the contact angle measurements, and this is obtained by analyzing the angle formed at the surface of a liquid droplet with a solid surface. This method provides insight about the surface free energy, addition and chemical modification of the surfaces. And the data is extremely important and required before you can provide the end user the confidence that the substrate which you are providing to them can be used in self cleaning, anti-fogging or biomedical devices. Then we have the compositional and elemental analysis techniques, which are EDX or EDS, is the technique which is used for elemental analysis and chemical characterization of the materials. What you do? You have an electron beam which strikes the sample, excites the electrons from inner shell, and that leads to emission of characteristic X-rays as the outer electrons fill the vacancies. And from measuring these emitted X-rays, you can find out the elemental composition, because every element has a given energy levels and you have a characteristic X-rays associated with it. You can use a inductively coupled plasma mass spectroscopy or spectrometer to analyze any trace or ultra trace elements across a sample. It is a method which is generally based on use of liquid based sample. So, you can have dispersion of solids in liquid, and the sample is actually then nebulized into a high temperature argon plasma where atoms are ionized. Now, these ions are then directed into a mass spectrometer, and hence they will immediately give you the information about the atoms which are constituting a given material based on the mass to charge ratio. So, it is a very accurate and high precision technique for determining the elements up to very low levels in the sample, and it is extremely useful in various areas which are making nanomaterials the basis of their growth. Then you have SIMS, again a surface sensitive analytical technique that provides elemental, isotopic and molecular information with very high sensitivity as well as spatial resolution. Here you bombard the sample with focused primary beam, and which sputters the secondary ions from the sample's surface, and you monitor the ejected ions using the mass spectrometer and then you can find out the composition about the samples. So, clearly it must be clear to you now that there are large number of techniques which are to be used to obtain information about the materials. Out of this sum of techniques which we have listed today, only a few could be discussed, and just imagine how many more are remaining. But we have tried to introduce to you some of the most commonly used techniques in the field of characterization of nanomaterials, and from the next lecture we will start discussing some of these techniques in more details, so that you develop the working capabilities to characterize nanomaterials and then move to the higher end techniques which are used for characterizing the nanomaterials. These are some of the books which you can follow to understand the techniques which were discussed today. So, I thank you for attending the first lecture of week 11. Thank you very much.